Hello everyone. Uh, in the last time, mm, yeah, in the last few lectures, we have been discussing this permutation group Sn, so which consists of this group Sn consists of all the bijections from the set 1 up to n to 1 up to n, and this forms a group under composition of functions. Okay, we have already learned few notions which are relevant in this context, or rather, we have introduced few notations uh, that helps us to deal with some of the these permutations and certain specific permutations in a reasonably neat manner. Uh, some of those are this cycle notation, and also we have learned this notion of cycle, and we have also learned this notion of transposition. Okay, so transposition is a cycle of length 2. Great. And we have also learned this notion of two cycles being disjoint. Okay, and you have learned that two disjoint cycles commute. Usually this proposition is summarized as uh, oops, sorry, disjoint disjoint cycles disjoint cycles commute. Okay, so today we'll learn certain further properties of these permutations and cycles, and more specifically transpositions and so on. I'm sorry. Yeah. So here is the first proposition, which states that any permutation can be expressed as a product of disjoint cycles. Okay, this is something that we have already seen in certain specific instances. For instance, for example, yeah, here we have been studying certain examples within this permutation group S5. Okay, in S5 we took this permutation and we showed that it can be written as a product of these two cycles, 1 comma 3 comma 5, and then 2 comma 4. Okay. And these two cycles are disjoint. Okay, recall that if we have two cycles a1 up to ak and b1 up to bl, they are said to be disjoint if these two sets a1 up to ak and b1 up to bl, they are disjoint. Okay. Okay, great. So we are trying to show that any permutation can be expressed as a product of disjoint cycles. Okay, the proof is essentially straightforward, and it's an adaptation of this argument. Okay, from in this computation, uh, from this computation it might not be that clear. It may not be that much clear to see why why any permutation can be expressed as a product of two disjoint cycles. But if you think for a while, then it will be so. So for instance here, so if you start with this element 1, okay, if you start with this element 1, uh, okay, and you write this one, okay, and next to 1 you write down the image of 1, next to 1 you write down the image of 1, which happens to be 3 here. Okay, so you write 3, and next to 3 you write the image of 3, which is which is 5, and next to 5 you write down the image of 5, which is 1. Okay, so this 5 comes back to 1, so then you close it. Okay, and then what's left? Maybe 2 is left, right? So we are within S5, so the set is 1. We are considering permutations of this. We have already considered 1 and 3 and 5, so 2 and 4 they are left. So let's see where does 2 go under this permutation. 2 goes to 4, so it will be 2 comma 4, and then where does 4 go? 4 goes to 2, so this has to be closed. So essentially this is the argument. Okay, but we need to be more precise. We are not working in S5. We are not working in S5. We are working in a greater generality. Yeah. So we start with an element a1 of the set 1 up to n. It could have been 1 for sure. Okay, and let's start with a1, and let k1 denote the least positive integer such that a1, k1 is the least positive. Is the least positive integer such that applying sigma to a1 k1 many times gives you a1 back. Okay, so okay, maybe I'll be just jumping around between these two pages. Here if you take this to be sigma, then if you apply sigma 3 times to 1, you get back to 1, okay, and 3 is the least such positive integer such that this holds, okay. So you apply sigma to 1 one time, then you get 3. If you add 2 time, you get 5, and if you add 3 time, you come back to 1 once again, okay. Yeah, and this is something that you just write down in a clean manner, okay. That's all. Okay, and since k1 is minimal, it follows that these integers are distinct. That is, a1 is image of its image under sigma, its image under sigma square, all the way to its image under sigma raised to k1 minus 1. These integers are distinct, and then if you look at this set, a1 sigma a1 till sigma raised to k1 minus 1 applied to a1, this is a set of size k1, and then if this set consists of all the integers between 1 up to n, okay, then sigma is exactly equal to this is clear, okay. And now if this is not the case, that is, if t1, that is this set, this bunch of k1 integers, if this bunch of k1 integers happens to be a proper subset of this set 1 up to n, then you choose some integer a2 from this set that lies outside t1, that is not in this list, okay. And so, okay, so that is, I mean, you choose one such integer, call it a2, and again look at the smallest positive integer k2 such that applying sigma to a2, such that applying sigma to a2 k2 many times gives you a2, okay. And now again by the same argument, or by the similar argument, by the minimality of k2, it follows that these integers a2 till sigma raised to k2 minus 1 applied to a2, these integers are all distinct, okay. Now if you look at this set, okay, and decide to call it t2, then you know that t1 and t2, they are certainly disjoint, okay, by our very construction. And here if you notice first that okay, so t1 and t2, they are disjoint. So what I'm trying to say is that these two cycles are disjoint. Why that is so, this is easy to see, but let's post on, or let's get into this argument right now maybe. uh, these two cycles are disjoint. If that is not the case, then some of this, that is, you will have sigma raised to I applied to a2, will be some of these, will be, that is, sigma raised to j applied to a1, okay. So this will happen for some I and j greater or equal to 0, okay. And from this you could obtain that a2 can be seen as an image of a1 under some power under some power of sigma, okay, under some power of sigma, and that will contradict the choice of a2, okay. And okay, so this shows that these two cycles, they have to be disjoint, okay. And so if you look at this, okay, so what I've just showed is that these two cycles are disjoint. Now if this bunch of integers and this bunch of integers all together give you 1 up to n, that is, if t1 union t2 is 1 up to n, then the permutation sigma that you have started with is equal to the product of these two cycles, okay. Great. And then you are done under this situation. And again, you need to now look at the situation when t1 and t2 all together doesn't give you all the integers from 1 up to n, and in that case we apply the same argument or the similar argument. We choose an element a3 from this set 1 up to n that is not among this list of integers t1 and t2, okay, and we look at the smallest positive integer k3 such that sigma applied to a3 k3 many times gives you a3 back, okay. And again by the minimality of k3, it will follow that this bunch of integers, they are all distinct, okay. And then we look at this set, we call it t3, and in the situation when this union happens to be 1 up to n, then one can show that the sigma is equal to the product of these cycles, okay. And it is also easy to see that this cycle is disjoint from the first two cycles that you have already considered, okay. If that is not the case, then sigma raised to I applied to a3 will be sigma raised to j applied to maybe a1 or maybe al, okay. So here l belongs to a1, a2, and again in that case one can check that a3 can be obtained from al by applying some power of sigma, and there is a contradiction to the choice of A3. Okay. Okay, great. And so we are done in this situation. Okay, when T1, the union of T1 to T3 is 1 up to n, and again, if that is not the case, we choose an element A4 from 1 up to n, lying outside this union, and follow the same style of argument to to show that to show what to show that this permutation sigma that you have started with can be expressed as product of disjoint cycles. And if you continue this process, okay, then this process has to stop because you have started with a finite set 1 up to n. Okay, and when this process has terminated, we will end up obtaining a decomposition of the permutation sigma that you have started with as a product of disjoint cycles. Okay. Now let me make few remarks about this proof. So the advantage of this proof is that one can apply this strategy. This proof is essentially algorithmic in nature. So one can apply this strategy in order to express any given permutation as a product of disjoint cycles. Okay. So this is something that we need to understand, because this is something that we will be applying at several instances, at several of the upcoming lectures. Okay, great. And let's try to provide an alternate proof that will not be that much illuminating. Okay, the reason is that okay, we'll be applying induction and okay, so I would say the previous proof that we have just discussed was more explicit in nature, that will allow you to express any given permutation as a product of disjoint cycles. Okay, whereas the algorithm is not that much clear from this proof. Okay, or is less clear. So we will apply induction on n to show that any given element of Sn, that is any permutation, can be expressed as a product of disjoint cycles. Okay. Yeah. Okay, so we start with S1. Inside S1, there is only one element, this one. Okay, this cycle. So this is certainly a product of disjoint cycles. And now we assume that any element of Sn can be expressed as a product of disjoint cycles for some positive integer n. Okay, then you start with an element sigma of Sn plus 1. Okay, so now if sigma of n plus 1 is n plus 1, then sigma can be thought of as an element of Sn, right? Because n plus 1 goes to n plus 1. So the first n integers 1 up to n, they're just permuted among themselves. Okay, so this permutation sigma can be thought of as an element of Sn. Okay, in other words, the restriction of sigma to this set 1 up to n gives us an element of Sn. Okay, and this element can be expressed as product of disjoint cycles. Okay, by the induction hypothesis. And then what? Yeah, so the permutation sigma that you have started with, when this equality holds, then its restriction to the set 1 up to n can be expressed as product of disjoint cycles by the induction hypothesis. Okay, now for k between 1 up to r, we look at this element tau k tilde. We already had this cycles tau 1 up to tau 2 up to tau r. We look at the element tau k tilde of Sn plus 1. Okay, which behaves same as tau k on the integers from 1 up to n, and it fixes n plus 1. Okay, when I is n plus 1. Okay, why are we doing this? We want to see these tau i's as elements of Sn plus 1. Okay, these tau i's, they're elements of Sn. Okay, so to extend this tau i's to think of this tau i's as an element of Sn plus 1, we introduce this permutation Tn tilde inside Sn plus 1, and this Tn tildes, they behave same as Tk tildes. This Tk tildes behave same as this tau k's. Okay, on the integers between 1 up to n, and this permutation tau k tilde, it fixes n plus 1. And then it follows that this permutation sigma is a product of this this permutations tau 1 tilde till tau r tilde. And yeah, and by our very construction of tau k tilde, and by the very nature of this tau i's, it is clear that this tau k tildes, they are cycles, and that they are disjoint cycles, because tau because tau 1 tilde is this, tau 2 tilde is this, and tau r tilde is this, and they are disjoint by their very choice, because you have applied the induction hypothesis to obtain disjoint cycles. Okay, great. So you have expressed sigma as a product of disjoint cycles. Then we are done under this condition when n plus 1 is fixed by sigma. So now you look at the situation when sigma does not fix n plus 1. So sigma of n plus 1 is not equal to n plus 1. Okay. And now you look at the transposition n plus 1 comma sigma n plus 1. This is a cycle of length 2 for the reason that these two integers are distinct. Okay. And now if you look at this product, sigma naught, sigma, I'm calling this transposition sigma naught. Okay. If you look at this product, sigma naught, sigma, if you apply this to n plus 1, then you obtain that this is n plus 1. Why? Because first you apply sigma to n plus 1, you get sigma of n plus 1. Now you apply sigma naught. So sigma naught stands sigma n plus 1 to n plus 1, you will get n plus 1. So now we are again back to the initial setup where we had a permutation fixing n plus 1. So now we have a permutation sigma naught sigma which fixes n plus 1. Okay. So it follows that sigma naught sigma can be expressed as product of disjoint cycles alpha 1 up to alpha s. Okay. So sigma naught sigma is the product alpha 1 up to alpha s. It follows that sigma is equal to sigma naught inverse times this product alpha 1 up to alpha s. Okay. And sigma naught being an element of order 2, okay, of the group Sn, it follows that sigma naught inverse is sigma naught. Okay. So we have sigma equal to sigma naught times alpha 1 up to alpha s. Now note that if each of the cycles alpha 1, alpha 2, alpha s fixes sigma n plus 1, then all of them are disjoint from sigma naught. Then this permutation sigma can be expressed, then this permutation sigma can be expressed as a product of disjoint cycles sigma naught times alpha 1 up to alpha s. So why that is the case? Because alpha 1 up to alpha s, all of them fixes n plus 1, okay, by the argument that we had here. This tau I tildes, they fix n plus 1, right? So here, where is it? Yeah. So here we know that sigma naught sigma can be expressed as product of these disjoint cycles, and this alpha i's, they fixes n plus 1. So this alpha i's, they also fix sigma n plus 1, then sigma naught will be disjoint from this all the cycles alpha 1 up to alpha s. Okay. So in that case, we are done in showing that sigma can be expressed as product of disjoint cycles under this hypothesis. And now we assume that at least one of this S cycles alpha 1 up to alpha s, they at least one of them does not fix sigma n plus 1. And now using the fact that the cycles are disjoint, it follows that exactly one of them does not fix sigma n plus 1. By rearranging or reindexing these alpha i's, we may assume that alpha 1 does not fix sigma n plus 1. Okay. So alpha 1 can be expressed in this form, sigma n plus 1 and then x1, x2 till xt with t at least 1. Okay. So now we note that these integers n plus 1 and then sigma n, this list of integers, this list of integers appended with n plus 1. Okay. So all these integers, they are distinct. Why that is the case? Because the permutation alpha 1 that you started with, it fixes n plus 1. Okay. Okay, great. So that's why n plus 1 cannot be any of this, because alpha 1 fixes this and alpha 1 does not fix any of them. Okay. And all these integers, any two of them are pairwise distinct. That is clear, because alpha 1 is a cycle, and when you write down a cycle, then in this form, then all these integers are distinct by convention. Okay. Okay, great. And so then we look at the permutation that you have started with, sigma naught sigma. So sigma naught sigma, okay, is equal to sigma naught alpha 1. So sigma naught alpha 1 is n plus 1 comma sigma n plus 1 and then alpha 1, and then we can write alpha 1 equal to the cycle by our choice. So alpha 1 is sigma n plus 1 and the next one till xt. Okay. And then we have seen it long back that such a cycle can be expressed as a product of product of transpositions. Okay, so we decompose this into this product, and so here we have got product of transpositions of very specific form. It starts with sigma n plus 1, and then x1, and then x2, and then xt minus 1, and then x n plus 1. The point is that the sorry, just give me a moment, trying to keep it turned on. Yeah, I think this the recording is in progress. Great. So we have sigma n plus 1, sigma n, I mean, all this transposition, one of the entries is sigma n plus 1. Okay, and that's why the product can be expressed as this form. So here in these two steps we have applied lemma 234. Okay, so this lemma was about decomposing a cycle as a product of transpositions. Okay, yeah, great. Then what is sigma? So sigma is sigma naught times alpha 1 up to alpha s, and sigma naught alpha 1 is this cycle. Okay, and this cycles, this first one sigma n plus 1 till n plus 1, and the next one up to xt in the middle. So this and this cycles alpha 2 till alpha s. Just give me a moment just to highlight, there has to be a comma here. Yeah, so all these s cycles, they are disjoint. Okay, and then it follows that we have just expressed the permutation sigma as a product of disjoint cycles in Sn plus 1. Okay, so then we are done with this alternate proof, which is obtained by applying induction on n. But the earlier proof was quite algorithmic in nature, and this can be used at any instance. Great. So let's try to apply this. Sorry. Let's apply the very first proof that we have discussed today to an element of S7, to this element, to this permutation. So we express this as a product of, we try to express this as a product of disjoint cycles. Okay, so we start with a1, some integer between 1 up to 1 up to 7. So we start with 1. Okay, so you start with 1 and then look at where does 1 go. You will see that 1 goes to 5. You will see that 5 goes to 1. Okay, under this permutation alpha that you have started with, 1 goes to 5, and then 5 goes to 3, and then 3 goes to 6, and then 6 goes to 1. Okay, so we have obtained this cycle, and then we choose an integer from 1 up to 7 which does not lie in this list, 1 5 3 6. So usually it's better to start with the smallest one, so we start with 2. Okay, great. So you start with 2, you see that 2 goes to 7, and then 7 goes to 2. Okay, yeah, earlier we have already had the cycle, and now you see that 2 goes to 7, and then 7 goes to 2. And what else among the integers 1 up to 7 is left out of this? I mean, other than all this 1 2 3 4 and then 2 6 integers, you'll see that 4 is left, and you'll see that 4 goes to 4. So you'll have just this. Okay, so we have expressed this permutation alpha as 1 5 3 6 times 2 7 times 4. Okay, so this is a cycle of length 4, this is a cycle of length 2, this is a cycle of length 1. Okay, and cycle of length 1 is trivial, right? There is no I mean, you can also ignore writing cycles of length 1. Okay, great. So we can also write alpha as 1 5 3 6 times 2 7. Okay, this product of how to call this length 4 cycle times that transposition, that is a cycle of length 2. Okay, so just as a small exercise, in order to familiarize ourselves better with the notions or the results that you have learned, we can try to compute the order of this element. And as I have stated long back as a caution, that whenever we write down a cycle, we need to specify in which permutation group we are working with. Okay, because for instance, if you look at this cycle, this could very well denote an element of S3. This could very well denote an element of S maybe 5. This could also denote an element in S100. Okay, so unless we specify the group in which you are working with, it is not clear what does a cycle written in this form denote. Okay, so here you have specified, so that is something necessary to do. I'm just trying to highlight that. So inside this group S11, we will try to determine this order, determine the order of this permutation. Okay, and this is left as an exercise. Okay, and let's try to discuss some of the implications or some of the corollaries of what you have already learned. Okay, we learned long back, I mean, okay, sorry, not long back, I was just referring to lemma 234. We have learned just a while ago that a permutation is a product of disjoint cycles, and maybe a long back or couple of slides back, we have learned that any cycle can be expressed as a product of transpositions. Okay, so let me repeat. We now know that any permutation is a product of disjoint cycles, and we know any cycle can be expressed as a product of transpositions. So we know by now that any permutation can be expressed as a product of transpositions. Okay, that is something interesting. Uh, for instance, okay, so let's try to discuss a bit about transpositions. Okay, we start with a positive integer n at least 3. Okay, and we pick to distinct. I'm sorry, we pick two distinct elements I and j from from 2 up to n. Okay, this is important. This is not a typo. I did not mean to start with 1. Okay, I want to take integers I and j larger than 1. Then if you look at the product of these three transpositions, you can see that this product is equal to the transposition I comma j. Okay, this is straightforward to see. Okay, so please try to show this equality, establish this equality. Okay, and can show that this holds inside this permutation group Sn. Okay, in fact, the argument is just here. If you apply this permutation to an element k, which is not 1, not I, not j, you will see that this will fix it. This will fix k, and this also fixes k. And then you need to apply this permutation, or rather both of them, to these integers, to 1 and then I and then j, to see that both of these two permutation, they behave in the same way on these three integers. Okay, and so from this equality we have just established that any transposition, any transposition I comma j, where I and j are greater or equal to 2, that can be expressed as a product of these transpositions, can be expressed as a product of transpositions of the form 1 2 1 3 1 4 till 1n. Okay, and if one of these two entries I and j is less than 2, that is one of them is 1, then